about the clubSandwich package, which is something that I've been kind of banging on for a number of years now. clubSandwich is it's a package that really tries to enhance some of the model fitting functionality that's available in other R packages. So it's an add-on that just gives you cluster robust standard errors and then associated methods for hypothesis testing, confidence intervals, and the like. And it's meant to be both easy to use and also to implement some what I think are useful refinements to the sort of typical approaches for doing cluster robust standard errors that make them kind of safer to use and so more accurate. So we've got some time today, so I'm gonna try to do a couple of things. First, I'll give kind of a flyby basic introduction to what is cluster robust variance estimation and the rationale for using it. Then I want to focus in on specifically on the use of cluster robust variance methods in the context of multi-level models. So for this part, I'm going to assume a little bit of familiarity with hierarchical linear modeling or multi-level modeling. And I wanted to do this here because this the combination of both multi-level modeling and cluster robust methods doesn't really get a whole lot of attention, and I think it's a useful technique. And then from there, I'll give you a little bit of an introduction to the small sample refinements, the adjustments that are implemented in clubSandwich that lead to better performance than typical methods. In this part of the talk, I'll also explain the origins of the package's name. And then finally, I'll wrap up with demos of a couple of the more recently implemented features in clubSandwich that I think are kind of slick if doing applied statistics is something that impresses you. I realize that may not be true for most of the world. Okay, so a little bit on the basics of cluster robust variance estimation. Let's think first about just a generic regression model. So we've got some outcome Y, we're regressing it on some set of predictors, X1, X2, X3, and so on. And then we've got an error term at the end, an EI. So this is, think back to, your statistics 101 course where you first learned about regression, or, maybe the first boot camp that you attended where you started to run regressions. In that first introduction to regressions, you probably learned it in the framework of two really pretty strong assumptions about the error terms in the model. We call these like maybe the classical regression assumptions. First assumption is that the errors are all independent, so that there's the correlation between the errors for different observations, say the EI and the EJ, that correlation is zero for all distinct pairs of observations. The other assumption is even stronger, which is, well, maybe equally strong, that the errors are homoscedastic, meaning the variance of each of those errors is constant and across all of the observations. So this assumption would be violated, for instance, if the variance of the errors, the spread of the errors, changes as a function of the predictors in the model. So maybe for one of your x's, small x's mean that you'll tend to have small variance. Large x's mean you tend to have larger variance. That would be a violation of the homoscedasticity assumption, or what people sometimes call heteroscedasticity. The thing is, once you get out of that first course, or outside of the confines of the homework problems or examples in that first course, there are a whole lot of situations where neither of these assumptions is plausible. For example, if you're working with data from a multi-stage survey, say where large-scale survey that sampled regions first and then sampled individuals within those regions, or if you work in education, maybe a survey where they first sampled schools and then sampled students within those schools. It's awfully implausible to think of those observations as being independent. Similarly, if you're working with longitudinal data or repeated measures experiments, or what some people call panel data, you're going to be dealing with violations of the independence and potentially also homoscedasticity assumptions. And then a third context, if you're more of an experimentalist or you're running A/B trials, if you've got cluster random assignment, where it's not the individuals that are randomly assigned to conditions, but groups of individuals, like in education, we do cluster randomized trials where whole schools are assigned to one experimental condition and a whole set of other schools are assigned to a control condition, and the outcomes are measured on the individual students within those schools. So these are just a couple of examples. There's probably hundreds of other use cases where the independence and homoscedasticity assumptions are not really going to be reasonable for a regression analysis. The point of the basic, the first takeaway here is that cluster robust standard errors, or what are sometimes called sandwich estimators, allow you to escape from these assumptions in a pretty convenient and kind of low effort way. So the idea here is that even if you've got violations of homoscedasticity or independence, you can still estimate a regression per normal, say using just LM that does ordinary least squares regression. And then use sandwich estimator or cluster robust variance estimation after the fact to correct the standard errors. The advantage of sandwich estimators is that they work under much weaker assumptions than the classical regression analysis assumptions. In particular, they work on the assumption that you can take the set of observations that you have and group them into distinct clusters. So we'll say that we've got, say, a bunch of observations, say that you can group them into J clusters, where the observations from within the same cluster are allowed to be dependent in a really kind of flexible, vague way, as long as the observations from different clusters, say a student in school A and a student in school B, there we'll still assume that those errors for those students are independent of each other. But if you've got two students from school A, their errors will allow, we're going to allow that their errors may be correlated with each other. And we'll also allow that the errors may be heteroscedastic. So the variance of the errors does not have to be constant across the range of the predictors. So just to drive this point home, these are really a whole lot weaker assumptions than the classical regression analysis. So all we're asserting is that the correlation between the errors from observations in different clusters are independent, but the correlations from observations within the same cluster can be correlated in kind of an arbitrary way, and the variance of the errors can also be varying. It does not have to be constant, also in a more or less arbitrary way. And if you're interested in getting sort of more of the in-depth treatment on cluster robust variance estimation, there's a really good long but easy to read, very meaty paper by Cameron and Miller from a couple of years ago that does a really comprehensive survey of cluster robust variance estimation methods. I should also say, so this technique is used in all sorts of different areas within statistics, and it was actually, it's like many things actually in statistics and maybe other areas of science. It was kind of just, it was invented or discovered multiple times by many different people. So this essentially the same technique is used in a lot of different applied fields. It goes under different names. If you're coming out of say economics, or if you have training in econometrics, you probably know these as the Huber-White standard errors, or just clustered standard errors. I know this is an R user user group, but if you've got any people that cross over to Stata, right, this is just VCE cluster. If you are working in sort of applied statistics, you might know these as cluster robust standard errors. If you come out of a biostatistics tradition, you might know this sort of area as generalized estimating equations from the famous Liang and Zager paper from '86. So, essentially the same methods were invented a bunch of different times by a bunch of different people. I would, since I'm sort of a mathematical statistician, or I came out of a traditional stats department, I want to give credit or a shout out to the original, what I think is the original origins of these methods in the survey sampling literature, dating back as far as the 1950s. So the folks that were working on the methods for essentially analysis of probability sample surveys. In that literature, the technique tends to be called linearization estimators. And it was, I think it was, the sense I have is that it was actually around, it had been invented for quite a while before anyone started to really write about it in academic research, because it was being applied in like public opinion polling organizations where it, before it sort of seeped into the academic literature. Okay, but I should tell you what these sandwich estimators actually are. So, okay, a little bit of statistics now. If we're thinking about a beta hat, so the estimated regression coefficients from an ordinary least squares fit. The actual variance, the true sampling variance of this beta hat is looks like this. And this is under the general assumptions that I talked about, where the errors are allowed to be correlated within clusters. So you can write the true variance like as in this formula here. Can you see this when I highlight things?
Yes. Oh,
good. Okay. Shout out to one person who's laughing at my jokes in the chat. So this is the actual form of the variance. The idea of the sandwich estimator, well, so the challenge with getting this, being able to estimate this variance formula is that it's got this thing in the middle, which is the actual variance of the errors. And we don't know this. We're trying to sort of avoid making strong assumptions about what the structure of this actual variance is, which means we've got to have some way to estimate it, but in a way that that doesn't impose strong assumptions. So the sandwich estimator does this simply by replacing this unknown covariance matrix of the errors with a function of the residuals from the regression. So if we say, we call this EJ here, call that the set of residuals for a given cluster. We're going to estimate the error variance by taking a cross product of those residuals, essentially like squaring them or multiplying the residual for student 1 in school A by the residual from student 2 in school A. So we multiply them within each cluster, and that gives us a really, really crude estimate of the variance or covariance of the observations within the cluster. It's really, really rough. That is like a really bad way to estimate the variances of individual errors or the covariances between errors from a given cluster. But the argument of the sandwich estimator goes, if you look at the formula on the bottom here, this is an average across a bunch of clusters, right? So we're taking a sum of some stuff and then dividing by the number of clusters. And so if the number of clusters is large enough, you say as it goes to infinity, or as it gets bigger and bigger, this bit in the middle is actually a consistent estimator of the true bit in the middle. Just by the weak law of large numbers, right? So averaging a bunch of stuff together, it will eventually converge to the truth under fairly general assumptions. So the idea here is that you can get away with using really, really crude estimates of the unknown errors, because we don't need to estimate individual errors. We just need to estimate this average of those errors. So as long as we can estimate the average by taking enough clusters and then relying on the weak law of large numbers, we get something that kind of works. We can think of it as like in the U.S. you can you might know bologna, right? Bologna sandwiches. Bologna is like the classic mystery meat, where the meat products that go into it, or like the ingredients of a bologna sausage, are not things that you want to think about too hard. They're not the highest quality, artisanal, carefully sourced, organic ingredients. You just sort of don't think about what goes into them. But the idea is, if you stuff enough of that filling into a sausage case, you get bologna. And it's, even though the individual ingredients are not high quality, you can still make a decent filling sandwich with it. So you can think of this plain sandwich estimator as kind of like a bologna sandwich. Right, the individual components in the middle of the sandwich are not the greatest, but you stuff enough of them together, you get something that works. And this is why they're called sandwich estimators. The formula here, someone thought at some point, looks like a sandwich. We've got this bread matrix on the outside, on either side, and then this stuff in the middle is the meat of the sandwich. That's where the name comes from. And I think, I would argue that this is again one of like the small number of actually cleverly well-named terms in statistics. Mostly statisticians are pretty awful about naming things, but this is one of the few exceptions, along with maybe jackknife, bootstrap, lasso, that kind of thing. So let me give you just an example of how you can do this with the clubSandwich package. I'm going to use just kind of a textbook data set. It's got repeated measures of students' mathematics performance, and it tracked students over time from kindergarten through 5th grade. It's a big data set, so it's got about 1,700 observations, but the observations are sampled from kids that are nested within schools. So we've got a dependence issue there, right? That you expect that students that tend to go to the same school, or students that go to the same school, will tend to have mathematics performance that is more similar to each other, right? More similar to students from the same school than they would be to students from other schools. All good statistics names are very American. Are American statisticians better? I don't think so, because I think there's plenty of sort of poorly named statistics terms that are attributable to Americans also. I think it's mostly just Brad Efron, right? The inventor of the bootstrap and the lasso, who was clever about this. Along with sort of usual sort of student demographic characteristic predictors, this data also has information on the size of the school, the percentage of low-income students in the school, and then an index that describes how mobile students in the school are, how much they move around from home to home. So here I've just done a bit of data cleaning, and then down at the bottom, I fit a regression with most of the predictors predicting math performance at a given point in time as a function of the student's grade level, the size of the school, the percentage of low-income students in the school, mobility, and then demographic predictors. And I'm going to focus on just the associations between the school level predictors and math performance. So how does school size predict the level of student mathematics performance? How does the proportion of low-income students in school predict mathematics performance, and so on? So, because of the nesting structure in this data set, we've got students nested within schools. We can estimate this regression. There might be reason to think, okay, well, the coefficients of the regression will be estimated just fine, but the standard errors are going to be really messed up because we've got dependence. And if we're also being sloppy and not checking the distribution of residuals and so on, we might have heteroscedasticity also. We can fix all that with a sandwich. We can make a bologna sandwich here. So I'm loading up the club sandwich package, and I will. So it's available on CRAN, and then here I'm creating a cluster robust. Excuse me, a cluster robust variance covariance matrix using the function vcov_cr for cluster robust. The first argument here is just the fitted model. Then we need to specify the clustering structure. So here we'd specify an ID variable that distinguishes observations from different clusters. Here in this data, the students are grouped by school. And so I use the school ID as the clustering variable. And then in the next line, I specify type equals CR0. CR0 is the plain bologna sandwich estimator with no sort of further adjustments to it. Then usually you wouldn't use the variance covariance matrix directly. You might use it to construct hypothesis tests or confidence intervals for the regression coefficients. And there's another function in clubSandwich called coef_test that gives you hypothesis tests for each coefficient. So coef_test takes the linear regression model as the first argument, and then you can feed in the variance covariance matrix. So the clustered variance covariance matrix, and there's some further options for the type of test that you want to run. Saying test equals Z just means I'm doing a basic large sample Z test. And coefs equals 7 to 9 means that I'm just going to look at the 7th through 9th predictor coefficients, which are school size, low income, and mobility, ignoring the other predictors in the output. So we can see of these three, the low income statuses, or the percentage of low income students in the school is the strongest predictor. It's the only one that's statistically distinct from 0. So low income is on a 0 to 1 scale. So 0 is like there's no low income students in the school. 1 is there's 100% low income students. So moving from no low income to all low income students leads to a reduction of, so comparing schools that are either have no low income students or all low income students, we'd expect their mathematics performance to differ by about 0.66 standard deviations. The other coefficients are associated as you'd expect, but they're not statistically distinct from 0 in this specification. So the methods that are implemented here, this plain sandwich estimator, is actually also available in other packages. There's a sort of famous and very widely used package called just Sandwich by Akim Sailais and some of his colleagues. Sandwich has been around for at least 16 or 17 years now. And it does all sorts of stuff. Sailais also just a couple of years ago included cluster robust variance estimation methods in that package, and implemented a bunch of other sort of robust variance estimation techniques as well. It's an incredible package. It was really the inspiration for clubSandwich in terms of the internal package design. And so what I'm showing you here is actually nothing special. You can do this with a sandwich package also. What's novel about the clubSandwich package is some of the small sample refinements that I'll get to in a little bit. Let me pause here if there's any questions or stuff folks are wondering about. Any of this sort of sounds familiar to you, or if you're trying to make connections between what I've just been ranting about and stuff that you know about. Vipin asks, how important is it to have evenly sized clusters? It's a really good question. I would say, the data that I'm dealing with here does not have equally sized clusters. And it's quite typical that you to work with clusters that are of varying sizes. Say, for example, a school that only has, say, where there's only 20 or 30 observations on students within that school, whereas other schools might have hundreds of observations in them. So cluster robust methods work even without equally sized clusters, although the plain sandwich estimator does not work as well. So if you've got very unequally sized clusters, some of the sort of adjustments and small sample refinements that I'll talk about in a little bit become more important. Another question, is the package integratable with the model summary package? Last I checked, it is. I think model summary supports clubSandwich, but you may want to double check on that for me. And then another question, can you have crossed dependence structures or multiple clustering variables? The clubSandwich package does not support cross-classified dependence structures. And there are other packages out there that do. As far as I know, those other packages are limited, though, to only implementing the plain bologna sandwich estimators. The main feature of clubSandwich is that it does these small sample refinements, and doing the small sample refinements is still an outstanding problem for cross-classified error structures. If someone has interest in working on that or has an idea about how to approach it, I would love to talk to you. Another question, does this sandwich estimator work also with interaction terms? Yes, it works generally with with any sort of regression specification that you would use for LM. Another question, does clubSandwich also integrate with multicomp? That is something I have listed as an outstanding issue with the package. If you're interested in helping with that, check my GitHub page. And then another question. So I described how to interpret the estimate from this display here. Can we interpret this like a raw data unstandardized coefficient, or should it be a standardized result? So I've the clubSandwich package works with the coefficients that it works with can be interpreted however you would interpret them in a normal regression analysis. Really, the only thing that the package is adding is getting the standard errors right. So if you set up your predictors to be standardized and your outcome to be standardized, then you can interpret these coefficients in standardized terms. Otherwise, you would interpret them as raw coefficients. So for example, the mobility index I've standardized. The interpretation of this coefficient would be, right, schools that differ by one standard deviation in this mobility index. Well, you would expect to have math performance that differs by about 0.12 standard deviations. So the answer there is use whatever techniques you're used to using for getting for setting the scale of the regression coefficients, and then feed this into clubSandwich to get the standard errors calculated appropriately. Okay, let me talk a little bit about using CRV for multi-level models. So in this section, I'm going to assume that you have a little bit of familiarity with multi-level modeling. So let's think now about sort of just a generic multi-level model for hierarchically clustered data. So now we have an outcome y for observation I in cluster J. So So this might be student I in cluster J. And multi-level models really have two parts to them. The first part is what you would call the fixed effect, or the systematic part of the predictor, where we're explaining the outcome in terms of some predictors, xij, times coefficient vector beta. Then we've got this other term here, plus zij uj. So this is these are the random effects. So there's some structure to the random effects that's expressed by the zij. So the structure for student I in school J, times a random error vector uj, which is a unique error that's associated with the cluster J. Say this might be just a random intercept for each of the schools for school J, or it might be like a random intercept plus a random slope for one or more of the predictors. So I think a lot of people who know the multi-level modeling literature, right, think of multi-level modeling as like a way to handle dependence or dependent observations. If you've got dependent observations like students nested within schools, instead of just fitting a regular regression model, we should be fitting a multi-level model that captures the dependence structure. So you might think of the multi-level model as like an alternative to cluster robust variance estimation methods. What I want to argue here is that you can actually combine the two, and it's useful to use both of these techniques together. So multi-level models make like regular sort of classical regression models, impose some pretty strong assumptions about the structure of the errors in the regression. So for the random effects, maybe random intercepts, or like a set of random effects, including random intercepts and random slopes, we would typically assume the set of random effects follows a multivariate normal distribution with mean 0 and variance covariance matrix tau. And then we might also assume that the individual level errors, say the error for E for student I in cluster J, is also normally distributed and homoscedastic, say with variance sigma squared. You can make other assumptions here, right? If you're used to using multi-level models for longitudinal data, you might say put some sort of structure on the errors, like say an autoregressive structure or something like that. Multi-level models can accommodate that pretty routinely. So typically, if you're using a multi-level model, though, the hypothesis tests or confidence intervals that you would calculate for the fixed effect component, for the beta coefficients, are based on, or they require, all of the assumptions of the model. So they require, that the random effects are properly specified, and they require that the structure of the individual level errors is also properly specified. I'm going to call that, so that sort of set of assumptions in the hypothesis tests, or standard errors, hypothesis tests, confidence intervals based on those assumptions, I'm going to call those model-based, meaning they are contingent on the proper specification of the model. So in addition to sort of having a properly specified model, the usual standard errors, hypothesis tests, confidence intervals are also based on large sample approximations. So we have to have like a large enough number of clusters in the data in order for those standard errors, hypothesis tests, and confidence intervals to work properly. Where I'm being a bit vague about what large enough means. So, multi-level models are a super cool tool, but like once you start to think more deeply about them, they're also like a huge source of anxiety. Like if you have to use these to actually draw conclusions about stuff, this requirement that you've correctly specified your model, or you've got at least an approximately correct model, is a big source of anxiety. Like why should you believe me that I've done a good job with specifying this model? And I'll sort of say more about what I mean by that and like why that should be anxiety-provoking in a minute. But first, let me tell you a little bit about how multi-level models are estimated. We'll need this just if you want to follow the technical details of the sandwich estimator. So multi-level models are estimated. You can think of them as being estimated really in two parts. The first part, we estimate the variance components, or estimate the parameters that have to do with the random effects structure and the individual level variance structure. Typically, people will use maximum likelihood estimation or restricted maximum likelihood estimation, REML, to obtain those variance component parameters. Once you've got those, right, that gives us a way to estimate the tau matrix, and then say the sigma squared, the variance of the level 1 errors. If we can estimate these parameters, we can then estimate our assumed variance structure for the errors in the model. So the variance of the set of observations from cluster I has this form here. It's this product of the z's times the random effects variance covariance matrix tau times the z, the structure of the random effects, plus sigma squared for each observation. So if the model is correctly specified, then this is what the variance of the outcomes of the errors looks like, and we can estimate that variance if we trust the structure of the model. I'm going to call this variance structure here VJ. So the variance of the errors for cluster J is a matrix VJ. Then in the second stage of estimating the multi-level model, we use this VJ, right, the estimated variance covariance matrix, to estimate beta, the fixed effect, or the coefficient vector. Rather than estimating beta by regular least squares, as we would with like just an LM model, multi-level models use weighted least squares, where the weights are the inverses of the VJ matrices. The inverse of the VJs, or inverse variance weighting, is kind of the optimal, most efficient way to do weighted least squares estimation, if the model is right. So the Betahat is actually looks pretty similar to ordinary least squares. It's still got this bread matrix out front, and then there's an x prime y on the back end. It's just that we're using the weights from the first part of the model, the VJs, to construct weights, and we put those in the middle. Okay. The advantage of using weighted least squares here is that it gives us more efficient estimates of the Betahats. So you'd expect the Betahats to have less sampling variability than if we had not used weighted least squares. And then finally, how do we say something about the uncertainty in Betahat? If we trust the structure of the model, if we trust our modeling assumptions, usually the way that you would estimate like the variance of Betahat is just to use this B matrix here. So the B matrix is a function of the X's, the predictors, and then the VJs, the estimated variance covariance structure. But this method of estimating the variance of Betahat is contingent on correct specification of the random effects and the level 1 error structure. And I would argue there's a lot of situations where we should be suspicious that we've got the correct model, or at least I would be anxious or worried that I've done something that I haven't got the model right. So let me try to get you worried. If you've taken a class in multi-level modeling, or if you've used these in your work, I kind of think of this next slide here as like the sort of nightmares that you might have, or the sort of problems that might keep you up at night, worrying about your multi-level model specification. So one thing you might be concerned about is that maybe you inadvertently omitted one of the random slopes from your model. Right? It's pretty typical when people do multi-level models to just use a random intercept specification where just the intercept term has a random effect on it. But what if the real, the true process has random slopes in it? Like one of the predictors should be varying from cluster to cluster. That means you've got an incorrect model specification, and you can no longer necessarily trust the standard errors from any of the for any of the coefficients in your model. Maybe you've got heterogeneous random effects. Typically, what people do with multi-level models is they assume that the set of errors for cluster J follows a normal distribution with variance covariance matrix tau. But what if the variance for some clusters is different than the variance for other clusters? Like you've got maybe say treated clusters and control clusters, and the variance in the treated clusters is different than the variance in the control clusters. That will lead to misspecification of your multi-level model. And again, you can't trust the uncertainty estimates from that model. What if you've got data that actually has 3 levels in it, but you're missing the second level? So it's actually a very common thing in educational data is we may have IDs for students nested within schools, but at least for primary schools in the US, right, those students are also nested within classrooms, nested within schools. And maybe we're concerned that students from that are in the same classroom in a school tend to be more similar to each other than students from 2 different classrooms in the same school. So there's this intermediate structure that creates dependence. But if we don't have the classroom IDs, we can't model it. So we're missing that. We're missing potentially a whole set of random effects that should be in the model, but we can't include because we don't have the proper data to understand the structure of students in classrooms in schools. So if we're in a situation like this, we've again potentially got a misspecified multi-level model. And then of course we can also, maybe we're also worried that we've misspecified the individual level error structure. Like instead of, so we're assuming homoscedasticity and no correlation in level 1 errors when the true process might involve heteroscedastic errors, and maybe there's some sort of structure to the correlation between observations at the individual level. Like with time series data, maybe we've actually got like an autoregressive process that we forgot to include in the model. So again, model is misspecified. We can't necessarily trust the standard errors or hypothesis tests or confidence intervals that come out of that model. Does any of this ring true if folks that use multi-level models? Is this stuff you've worried about ever, or I'm not asking for confessions, I'm just curious. Truly the stuff of nightmares. Yeah. So if we're in a situation where we're worried about misspecification of a model like this, the same argument that works for regular regression estimation, you're using sandwich estimation for regular regressions, also holds here, where we can use sandwich estimation methods to correct the standard errors and so assess the uncertainty in our regression coefficient estimates without relying on the strong assumptions of the multi-level model. So before I get there, a question from Diego: Are there situations where the model, like the fixed effect Betahat estimates, could be biased if the structure is misspecified? It's a really good question, and there are situations where that's true. Like there are I haven't sort of gone into the assumptions of the multi-level model here, but like, one of the critical assumptions of the multi-level model is that, so let me just get back to here. One of the big assumptions of the multi-level model is that the random effects, the UJs, are not correlated with the systematic predictors, the XIJs. If there's correlation there, then using a multi-level model like this can lead to biased estimates of the beta hats. Cluster robust variance estimation methods or sandwich estimators are not going to fix that. So we're still going to require that the assumptions where you would use a multi-level model, that those assumptions hold. It's just that, so yeah, they're not a panacea here. So, and the concern about assumptions like correlation between the random effects and the predictors is like the remedies for that are things like being careful about centering the systematic predictors properly to avoid correlation. So I'm going to sort of assume that you've done that and that you can trust the beta hat estimates from the multi-level model, but you don't necessarily trust that you've gotten the random effects specification and the individual level error specification correct. So say that maybe the true process follows some other structure. I'll call it OmegaJ, where that structure OmegaJ doesn't necessarily conform to the assumptions of the model. In that case, you can work out approximately what the true variance covariance of the beta hats is. So we again get something that looks like a sandwich. It's just got this unknown error structure in it. And we can use the sandwich estimation technique of substituting the cross product of the residuals from a cluster to get a crude estimate of the real unknown error structure. Because the meat in the middle of the sandwich is again an average, we can rely on the weak law of large numbers to get a robust variance estimation or variance matrix, as long as the number of clusters is large enough. So this is what you would call a plain bologna sandwich for a multi-level model. And the clubSandwich package supports cluster robust variance estimation methods for multi-level models like this. For models that are fit using the LME4 package, as well as the LME function from the NLME package. That's the older package for fitting linear mixed effects models. So here I'm again using the data from the sustaining effects study. I fit the same model specification, but now I'm including random effects for school, or random intercepts for each school, random intercepts for each child. This is not a carefully constructed model. I just kind of threw in the random intercepts to acknowledge that there's structure here. And I guess maybe particularly because I've been sloppy about specifying my random effects, we should be, we should not trust that I've got a correctly specified model here. But we can use cluster robust methods and get a sandwich estimator for the coefficients from this model that doesn't require having a properly specified model. So here I'm using the conf_int function, which works very similarly to the coef test function. You feed in the fitted model, in this case a multi-level model, specify the robust variance covariance matrix, or here I'm using a sort of a shortcut where instead of estimating the variance covariance matrix and then feeding it into this argument, I'm just saying which type of variance covariance matrix I want. CR0 is the plain bologna sandwich estimator. Test equals Z is the large sample Z test. Yeah, and then the function will give us confidence intervals for each of the regression coefficients that we're interested in. So here I'm focusing on the school level predictors. And in this particular case, the cluster robust variance standard errors are not too different than the model-based standard errors. So there's actually hardly any difference, except for the mobility coefficient, where the robust standard errors are a little bit bigger, potentially because I'm missing a random effect on that predictor, or there's some sort of heteroscedasticity or something like that going on. The thing is, though, right, the plain bologna sandwich estimators rely on having a large enough number of clusters to give us trustworthy standard errors. And there's often situations where it's kind of hard to gauge whether we've got a big enough sample. Here I've got 60 schools. You might think 60 is a big number. We should be fine with these plain bologna sandwich estimators. But it's kind of hard to tell, it turns out. So let me now tell you a little bit about some of the small sample refinements that are implemented in clubSandwich, and that are really like this is where the comparative advantage of this package is. The problem with plain bologna sandwich estimators is that they require a large enough number of clusters. If you don't have a sufficient number of clusters, the standard errors actually tend to be too small. They don't properly capture all of the uncertainty. They have a downward bias. And because of that, hypothesis tests tend to have inflated type 1 error rates. Confidence intervals have less than the advertised level of coverage. So they're narrower than they should be. And what makes this particularly sort of vexing is that what counts as the large enough number of clusters to trust the plain sandwich estimator depends on the number of clusters, not the number of observations. And it also depends on the configuration of the predictors. So if for different X matrices, you may have a large enough number of clusters or not a large enough number of clusters, depending on sort of features of the covariates or the predictors. And that makes it hard to tell, makes it quite hard to tell whether the plain sandwich estimator really works or not. So you might say, how can you tell whether your plain bologna sandwich estimator is really edible? So clubSandwich does two things to try to remedy this issue. One is that it implements what you might call like a fancier sandwich estimator. The fancy sandwich involves including little adjustments to the residuals that are used in calculating the meat of the sandwich that give us a variance covariance matrix that is close to unbiased under a certain working model. So the form of the adjustments looks like this thing here, where this is just the regular sandwich estimator, but it's got these AJ matrices in it. So these are little adjustment matrices that tweak the residuals and give us something that is close to unbiased, but still noisy. So that and this is the motivation for the name of the clubSandwich package. If this whole thing is a sandwich estimator, but now we're putting extra stuff into the middle of the sandwich. It's kind of like we're stuffing extra Swiss cheese, sprouts, pickles, mayonnaise in with the meat of the sandwich, and we end up with a club sandwich rather than a plain bologna sandwich. The adjustment matrices are constructed in such a way that if we've got the model correctly specified, then this robust variance estimator is exactly unbiased. Now you might think that's a little bit weird, right? The whole point of cluster robust methods is that they should work well even if we don't have a correctly specified model. So now you're telling me we need to have a correctly specified model to get exactly unbiased sandwich estimators. So there's both theory and now a lot of simulation evidence to support the assertion that the model doesn't actually have to be correctly specified in order for these adjustment matrices to really work quite well. So even if the model is not properly specified, or it still has some missing random effects or some heteroscedasticity, some other form of misspecification, these adjusted sandwich estimators have drastically reduced bias. So they help a lot, and they perform really, they give you close to unbiased estimates, even with quite small samples. So that's one of the adjustments implemented in clubSandwich. The other is a degrees of freedom adjustment. So to this point, I've been demonstrating hypothesis tests that use large sample like z-tests or normal approximations. clubSandwich also implements what's called a Satterthwaite degrees of freedom adjustment for hypothesis tests and confidence intervals. You can think of this as, so if you've go back to like stats 101, where you learn the t-test allowing for unequal variances. It's sometimes called the Welch-Satterthwaite t-test. That Welch-Satterthwaite t-test uses this other degrees of freedom in the construction of the test. And the Satterthwaite degrees of freedom implemented in clubSandwich are essentially like a generalization of that Welch-Satterthwaite technique. And there's further generalizations of that technique for conducting multiple contrast hypothesis tests, like the sort of F test that you would do in model comparison or analysis of variance. There's generalizations that we've called the approximate Hotelling's t-squared test that work similar to Satterthwaite approximations. And these degrees of freedom mean that the hypothesis tests work well in the sense of having the correct type 1 error rates and confidence intervals with advertised coverage levels, even when the number of clusters is quite small, and even when the working model is not entirely correctly specified. The really useful thing about these degrees of freedom is that they're diagnostic. So if you have low degrees of freedom, that tells you you're in a situation where you can't trust the large sample approximations. And it tells you further that for this data, there's very little information available to estimate the variance of model coefficients. So you're in a situation where the sort of asymptotic or large sample approximations just don't work very well. So you can really like read the degrees of freedom as telling you whether this sandwich estimator is whether you can trust it. If you have extremely low degrees of freedom, then you want to be wary. Once you've got above about 5 or 6 degrees of freedom, you can have some confidence that the small sample adjustments implemented in clubSandwich will work well. They'll give you tests with proper coverage levels. Here, let me just give you an illustration of the difference between the plain bologna sandwich estimator and these small sample refinements. So at the top, I've done hypothesis tests for that same set of coefficients using the bologna sandwich, CR0, and using large sample z-tests. At the bottom, I'm using the small sample refinement, which is called CR2, so the cluster robust type 2 adjustments, and then the Satterthwaite degrees of freedom adjustments. So comparing these two, you can see that at the bottom, the standard errors generally just go up a bit to correct for the downward bias in the plain sandwich. And then rather than using like infinite degrees of freedom, which is what you would do in a large sample z-test, we use the Satterthwaite degrees of freedom. And the Satterthwaite degrees of freedom are adequate here. They're not super large, right? They're 17, 18 degrees of freedom, which is enough to mean that like you can't necessarily that there will be some difference from the large sample tests. If we were down to like say 7 or 8 degrees of freedom, which can happen, then there can be big differences in confidence intervals between the large sample test versus the small sample adjusted test. The other thing to note about these is that the degrees of freedom are specific to the coefficient in the model. right? Each of these predictors here has a distinct degrees of freedom, which is different than sort of how you think about degrees of freedom in classical regression or multi-level modeling. Here's just an illustration of how much a difference this makes. So at the top in the red is the large sample model-based confidence interval. Doing like a small sample adjustment from the Elmer test package hardly makes any difference with these data. The blue is the large sample cluster robust confidence interval. And then the purple is the small sample adjusted confidence interval. And you can see they're just bumped out a bit. That indicating that, right, the small sample adjustment is really needed to give a fully sort of honest representation of the uncertainty in these coefficient estimates. So I've gone, I got excited, I guess. I've gone longer than I was expecting to. So let me just kind of wrap up by giving you a quick sense of all of the features of clubSandwich. For today, I focused on sandwich estimators for linear regression and then also for multi-level models. clubSandwich supports both of those for models fit using the LM function in R, as well as the LME function from the NLME package, and then Elmer from the LME4 package. It also works with a whole bunch of other types of models that can be fit using different packages in R, and where the same sort of sandwich estimation technique applies. So you can do this as well with generalized least squares models with the GLS function, for generalized linear models with GLM, as well as multivariate regression, two-stage least squares, instrumental variables models with the IVReg function, panel data models from the PLM package, as well as a variety of models that are used for meta-analysis, the meta-4 package, the RoboMeta package. And this is, right, clubSandwich supports these actually because I got interested in all of this stuff originally, thinking about it in the context of meta-analysis. So clubSandwich actually started as something that was mostly focused on meta-analysis, and then we kind of built it out to cover all of these other models because they essentially have the same structure. They work with the same sort of techniques. Similar to the sandwich package, clubSandwich it has an object-oriented design, which makes it possible to extend it. If you've got say a different type of model that's not currently supported in clubSandwich, but where we can figure out what the right components of that model are to feed into clubSandwich, we can make it work for other types of models. In fact, I've gotten requests for a number of other types of models where it would be useful to have clubSandwich standard errors. So I have now a pretty healthy to-do list of further directions for extending the package. If you have ideas about that, or if there's sort of models where you'd like to see extensions, feel free to hit the GitHub repository for the package and leave a comment or a suggestion. And as I sort of indicated, the package is still under active development. So it's been available on CRAN now for a number of years, but I'm still developing it. I just recently threw up a package website that has like the web documentation with the package down format, which is really nice. And then the whole source code and everything is on GitHub. There's issues on GitHub. You're welcome to add issues, add suggestions, feature requests, or if you're interested in contributing to the package, I do also welcome pull requests, or as well as questions, just discussion about future directions. I think I'll leave it there. I'm going to skip these few final thoughts and just say thanks for your attention. And I see a couple of questions in the chat, so maybe we can move to questions from here. Let's see. So question, what if I use a standardized effect size whose data were already adjusted for a small sample size, such as hedges G? When I process multiple G effect sizes for CRV, this is also adjusted for a small sample size. Is this double adjustment for a small sample size? Okay, yeah, so this question from Nick Young here is, it's kind of specific to meta-analysis. And it's a good question, right? The terminology here can be a little bit boggling because there's all sorts of small sample adjustments going on. So the small sample adjustment for hedges G pertains to the sample size for the primary study on which the effect size was calculated. So there we're really talking about, say, one of the studies included in your meta-analysis, say, only has 14 participants in it. So you need to use that small sample adjustment to get a close to unbiased effect size estimate. That's the small sample adjustment that goes into hedges G. The small sample adjustments that I was talking about here and that are implemented in clubSandwich are really about the number of clusters in the meta-analysis model. So say in the context of meta-analysis, usually clusters means studies. So the small sample size means in that context, the number of studies that are included in the analysis. If you're doing a meta-analysis that only has, say, 20 studies in it, then you should be worried about using the small sample adjustments for cluster robust variance estimation. So essentially, even though this you might think there's this double adjustment going on here, you need to do both in order to control the biases in the meta-analysis, like average effect size estimates, and then the biases also in the robust standard error estimates. Another question from Nithin, any resources for learning in detail about these estimators? I'm happy to post my slides. I'll put them on my website and then maybe send a link to Henrik. But there's this paper by Cameron and Miller that does I think an excellent, really thorough job of explaining the sandwich estimation methods. It does also cover the small sample adjustments that I discussed today. There's also the clubSandwich package includes a couple of vignettes about that address using cluster robust methods in different contexts. So there's one vignette that's about using these methods for meta-analysis. There's one vignette that's about using them for panel data analysis or longitudinal data analysis. And there's one about conducting hypothesis tests, like F-type hypothesis tests. So it's been on my to-do list for quite a while, but I promise I haven't forgotten. One of my goals is to write a really extensive tutorial introduction to sandwich estimation that explains all of the different adjustments that are implemented in clubSandwich, and also explains kind of like the under the hood details of the derivations behind the adjustments, and then the mathematical details around how they're, and actually computational details around how the calculations are actually implemented in clubSandwich. But this is sort of a classic hobbyist package developer problem, that you get really excited about building in lots of features and neglect the documentation side of things. But I'm pretty responsive on email and on GitHub. So if you have questions or you encounter problems with using the package, you're also welcome to hit me up there.